Today we're going to talk about polygons, and polygons are simple closed figures formed by 3 or more line segments called sides. Now in the last video we talked about a specific type of polygon called a triangle, and now we're going to talk about all other types of polygons. So what makes a polygon? A polygon, it has to be closed, there cannot be overlapping sides, and all the sides have to be line segments. So you can see some non-polygons here. This first one that looks like a piece of pizza is not a polygon because it has a curved sides. The middle one is not a polygon because it has crossed or overlapping sides. And the third one is not a polygon because it is open. The sides are not connected. So what types of polygons do we have? Polygons are classified by the number of sides and angles that they have. A polygon will always have the same number of angles as it has sides. So here are the first 10 polygons, my bad. The triangle, quadrilateral, pentagon, hexagon, heptagon, octagon, nonagon, decagon, undecagon, have you ever heard of that? And dodecagon, the first names of our polygons. After this, it gets a little ridiculous what they're called, so we usually just refer to anything beyond this as the number of sides that it has, followed by the word gon. So the next one we would probably just call a 13gon, a 14gon, and so on and so forth. You know, an 82gon would be a polygon with 82 sides, so on and so forth. Because there are actual names for these, but they're a bit tongue twisters and hard to pronounce, so it's just best that we name them by the number of sides that they have. Are these shapes polygons? Well, looking at the first one, all the sides are line segments, they are connected, and there are no overlapping sides, so yes, this is a polygon. What kind of polygon is it? Well, if you count the number of sides that it has 1, 2, 3, 4, 5, 6, 7 sides, so this would be classified as a heptagon. Sometimes called septagons. Hepta and septa both mean 7. The next one, is this a polygon? All the sides are line segments. None of them are curved. It is closed. No overlapping sides. Yes, this is a polygon as well. What kind of polygon is it? If you count the sides, 1, 2, 3, 4, 5, 6 sides. This is a hexagon, folks. And this last one here, no, this is not a polygon. It has a curved side. It does not get to be part of the polygon party. So that's what a polygon is and how to determine if something is a polygon and name polygons by their sides and by their angles. Next, we're going to talk about angles in polygons. Well, we talked about triangles, and we know that a triangle has a sum of 180 degrees. All the angles add up to 180 degrees. So I know there is a grand total of 180 degrees in a triangle. But what about other polygons? How many degrees are there in other polygons? Well, if we examine each polygon and figure out how many triangles there are in each one of these polygons, we can then figure out how many degrees there are total. So if you look at a quadrilateral, so here I have a square, and this red dotted line kind of cuts it into 2 separate triangles. So there are really 2 triangles inside of a quadrilateral, and each one of those triangles has 180 degrees. So 180 times 2 is 360. So a quadrilateral will have 360 degrees in it. And then if we look at the pentagon, you can see that we can kind of cut a pentagon into 3 triangles. And again, each one of those triangles has 180 degrees. So if we take 180 times 3, we get 540 degrees. So every pentagon will have 540 degrees as its angle sum. And if we look at the hexagon, we can see we get 4 triangles inside of it if we cut it up. And again, every triangle has 180 degrees. So 180 times 4 is 720. So we can kind of see a pattern here. We can kind of see how to determine how many degrees there are in a polygon by just knowing how many triangles fit inside of it. Well, how do you figure out how many triangles fit inside of it? Well, we're going to use something called a diagonal. And a diagonal is a line segment that connects 2 non-consecutive vertices in a polygon. Basically, it's cutting the shape into triangles like we just did. So if we notice, a quadrilateral has 4 sides and 2 triangles. A pentagon has 5 sides and 3 triangles. A hexagon has 6 sides and 4 triangles. And an octagon, so we skipped some here, an octagon has 8 sides and 6 triangles. So what do you notice about the relationship between the number of sides something has and the number of triangles it has? Well, the number of triangles in a polygon is always 2 less than the number of sides that it has. So if we call the number of sides that it has n, how many triangles are there going to be in that polygon? N minus 2. There will always be 2 less triangles than there are sides. So then how do we figure out the total degrees in a polygon? Well, every one of those triangles is going to be 180 degrees. So if we just multiply that by 180, that will tell us how many degrees there are inside of a polygon. So that's our interior angles of a polygon. It says the sum of the degrees of the interior angles in a polygon with n sides is always n minus 2 times 180. N minus 2 times 180 will tell us how many degrees there are in any polygon without having to have a picture of it. So look at these two problems here. We don't have pictures of the polygons, so we can't really cut them up into triangles physically, but now we know how to figure out how many triangles there are in the shape. So what is the sum of the interior angles of an 18gon? So this is a polygon that has 18 sides. So how many triangles would there be in an 18gon? Well, it'll be the number of sides minus 2. And if we take that times 180, that will tell us the sum of all the angles in an 18gon. So let's figure that out. 18 sides minus 2 times 180. So that's 16 times 180. And that gives us a total of 2,880 degrees. So the sum of the interior angles of an 18gon will be 2,880 degrees. That's a lot of degrees. Next one, what is the sum of the interior angles of a decagon? Now a decagon, if you'll remember from a few slides ago, has 10 sides. So how many triangles are there going to be in a decagon? That's n minus 2. And we're going to take those times 180. So it has 10 sides minus 2 times 180, so that's 8 times 180, and that is 1,440 degrees. So the sum of the angles in a decagon is 1,440 degrees. That's how to find the sum of all the angles in a polygon. A regular polygon is a polygon with all equal sides and all equal angles. These are usually the ones that we're used to seeing. So when we think of a triangle, we might think of an equilateral triangle. That would be called a regular triangle as well. It has all equal sides and all equal angles. And when we think of a quadrilateral, we might probably think of a square. It has all equal sides and all equal angles. So we know that the triangle has an angle sum of 180 degrees. And if each angle is equal, well, 180 divided by 3 equally is 60 degrees. So every angle in a regular polygon is going to be 60 degrees. Likewise with our quadrilateral, if it's a square, we know the sum of all the angles is 360 degrees. And if we take 360 divided by 4 equally, you get 90 degrees. So every angle in a regular quadrilateral, aka a square, is going to be 90 degrees. Well, what about the pentagon? What is the measure of each interior angle in a regular pentagon? What is each one of these interior angles going to be if they're all equal? Well, we can use the sum of the angles to help us find what each individual angle has to be in a regular pentagon. So I know the sum of the angles is going to be n minus 2 times 180. And a pentagon has 5 sides, so 5 minus 2 times 180. That's 3 times 180, or 540 degrees. Oops. Is the sum of all the angles. So what is just one of the angles going to be? Well, there are 5 angles that are equal in a pentagon. So I'm going to take 540, maybe 540 divided by 5 to get what each angle needs to be. And 540 divided by 5 is 108 degrees. So in a pentagon, every angle is going to be 108 degrees exactly. And that will get me a regular pentagon. So that's how we can use the angle sum to find what each angle is individually. So here, to find the measure of a single angle in a regular polygon, we're going to find the sum of the angles, and that was n minus 2 times 180. And we're going to divide it by the number of angles that it has, which is just n, because if it has n sides, it's going to have n angles as well. So let's try it here. What is the measure of each angle in a regular octagon? So if we were trying to create a regular octagon, looks like a stop sign, what is each interior angle going to be? So we have to find what the sum of the angles is going to be, n minus 2 times 180. And we're going to divide that by the number of angles that we have, which is n. And in this case, n is 8. 8 minus 2 times 180 divided by 8. That gives me 6 times 180 divided by 8. And 6 times 180 is 1080 divided by 8 is 135 degrees. So every angle in a regular pentagon, or sorry, octagon, is going to be 135 degrees. So now we can name our polygons. We can find the sum of all the angles in a polygon. We can find what each individual angle in a regular polygon is. And then lastly, we want to talk about tessellations. Now, a tessellation is a repetitive pattern of polygons that fit together with no overlaps or gaps. So you can think of it like tiles. If I was trying to tile a floor or tile a wall, and I didn't want any gaps or overlaps, I don't want my tiles to overlap, and I don't want any spaces in between them, that's basically what a tessellation is. So here are a few examples of tiling or tessellations. And we see tessellations here with equilateral triangles in the first example. We see tessellations with regular hexagons, how they fit together nicely. And then here we used a combination of shapes, octagons and squares, to create kind of that tiling pattern. So that's what a tessellation is. So will all polygons create tessellations? Can I create a tile floor with any type of polygon? Well, some of them do. As you can see here, squares easily work. That's why most tiles are squares, because they fit together very nicely and very well. However, if I try to tile a floor with regular pentagons, it's not going to work. You can see that there's a gap created that I can't fill in with another pentagon, a regular pentagon of the same size. So no matter how I arrange these pentagons or try to fit them together, they're not going to create a tiling effect. They're not going to create a tessellation. So how do I know if a shape is going to create a tessellation or not? Well, the sum of the angles at each vertex, where they come together, must be 360 degrees. They must be able to complete a full 360 degrees so that there's no gaps. So an easy way to tell is to tell if 360 is divisible by the angle measure, it will create a tessellation. So in the examples that I showed here, the squares, 360 is divisible by 90 degrees. 4 times 90 is 360. So when I put these 90-degree angles together, I'm going to create a full 360 degrees perfectly. So they're going to fit together with no gaps. Here we have some triangles that have 45-degree angles in them. And each 45-degree angle, when I put them together, if I put 8 of them together, I'm going to get 360 degrees exactly. So it creates that full tile with no gaps or overlaps. So will a regular octagon create a tessellation? Well, we saw a couple of slides ago that a regular octagon, each angle is 135 degrees. So if I try to fit multiple 135-degree angles together, is it going to create that full tile or that full 360 degrees with no gaps or overlaps? Well, I just have to check to see if 360 is divisible by 135. And if you do that, you get 2 2/3. So it does not come out evenly. So will we be able to create a tessellation with regular octagons? No. 360 is not divisible. Divisible by 135. So that's a pretty easy way to tell if a shape will create a tessellation.